These are the notes for 3.4 complex numbers part 2. So yeah, like I said, we were going to spend a few days on complex numbers. So this is the second day of that. So yesterday we talked about adding, subtracting, and multiplying. Today we're going to talk about dividing, and in order to divide complex numbers, we need to talk about complex conjugates. Two complex numbers of the form a plus bi and a minus bi, where b does not equal 0, are called complex conjugates. The product of complex conjugates is always a real number. Once again, the product of complex conjugates is always a real number. For example, 3 plus 2i times 3 minus 2i. These two numbers, complex numbers, are complex conjugates of each other because they have the same a value, they have the same b value, and one's plus and one is minus. Therefore, I know they're conjugates. So if I multiply these, I should get a real number. So let's see if that happens. If I FOIL, 3 times 3 gives me 9. 3 times negative 2i gives me negative 6i. 2i times 3 gives me 6i. And then 2i times negative 2i would give me negative 4i squared, which would be negative 4 times negative 1, which gives me positive 4. My imaginary values cancel each other out, so I'm just left with 9 plus 4, which gives me 13. So as we can see, anytime we multiply complex conjugates, we get a real number. We can use this fact to write the quotient of two complex numbers in standard form by multiplying the numerator and denominator by the conjugate of the denominator. So that's a key right there, multiplying the numerator and denominator by the conjugate of the denominator. Anytime we're dividing two complex numbers, this is what we want to do. We want to find the conjugate of our denominator, then we're going to multiply the top and the bottom of the fraction by that conjugate. So let's look at some examples. Letter A says 4 plus 3i times 1 minus 2i. So once again, I want to find the denominator, the conjugate of the denominator. So my denominator is 1 minus 2i. In order for it to be a conjugate, I need it to be the same a value, same b value, and one adding, one subtracting. This one's already subtracting, so I know this one needs to be adding. There's my conjugate of my denominator. So I'm multiplying the top and the bottom of my fraction by 1 plus 2i. And then all I do from there is I FOIL the numerators. So 4 times 1 gives me 4. 4 times 2i gives me 8i. 3i times 1 gives me 3i. And then 3i times 2i gives me 6i squared. Or we can just say minus 6, since I squared equals negative 1. Now I need to FOIL my denominator. 1 times 1 gives me 1. 1 times 2i gives me 2i. Negative 2i times 1 gives me negative 2i. Negative 2i times 2i would give me positive 4. Because it would be negative 4i squared. So negative 4 times negative 1 gives me positive 4. Up top, combining my real parts, 4 minus 6 gives me negative 2. 8i plus 3i gives me 11i. Downstairs, my imaginary numbers cancel each other out, and I'm left with 1 plus 4, which gives me 5. I can now split these into their own fractions. I can give each term their own denominator, so that'd be negative 2/5 plus 11i over 5. Neither one of these fractions can be simplified any further. It's also in standard form for a complex number because my real part comes first and my imaginary part comes second. So there would be me dividing my two complex numbers and writing them in standard form. So let's look at letter B. Once again, I want to find the conjugate of my denominator. Conjugate of the denominator would be 2 minus 3i. So I'm multiplying the numerator and the denominator by 2 minus 3i. Foiling the top, 1 times 2 gives me 2. 1 times negative 3i gives me negative 3i. Negative 4i times 2 gives me negative 8i. Negative 4i times negative 3i gives me negative 12, over 2 times 2 gives me 4. 2 times negative 3i gives me negative 6i. 3i times 2 gives me 6i. And then 3i times negative 3i gives me positive 9. Because once again, that'd give me negative 9i squared. I squared is negative 1, so negative 9 times negative 1 gives me positive 9. Up top, my real parts are 2 minus 12, which gives me negative 10. My imaginary parts are negative 3i minus 8i, which gives me negative 11i. Once again, downstairs, the imaginary part cancel out. 4 plus 9 gives me 13. I can then split these into their own fractions. Negative 10 over 13 minus 11i over 13. Neither one of these fractions can be simplified. They are also in standard form because the real part comes first and the imaginary part comes second. So let's look at letter C, the last problem on this slide. So I have 2 plus 5i over 4i. I have to determine the conjugate of my denominator. It looks a little different because there's not a real part to it. If I wrote that with a real part, it would be 0 plus 4i. So the conjugate of that would be 0 minus 4i, or just negative 4i. So I'm multiplying the top, and the bottom by negative 4i. So I get 2 times negative 4i, which is negative 8i. 5i times negative 4i would give me negative 20i squared, so plus 20, over 4i times negative 4i would give me positive 16. Get negative 8i over 16 plus 20 over 16. Now there's two things wrong here. One, I can simplify both of my fractions. And two, I need to write the real part first and the imaginary part second. So I'm going to combine both my steps. I'm going to go ahead and simplify my real value, and I'm going to put it in its correct place. 20 over 16 would reduce down to 5 over 4. And then negative 8i over 16 would reduce down to negative I over 2. Neither one of my fractions can be simplified any further, and it is now in standard form. Hopefully this is making sense. I feel like it's not too bad. Once again, as always, if you have questions, feel free to ask. Now let's talk about solving quadratic equations. If I gave you x squared equals 25, to solve that you would take the square root of both sides. when I'm taking the square root of 25, I'm asking myself, what number times itself gives me 25? Most of y'all would just say that it is 5. 5 is a correct answer. But is that the only number that when I multiply it by itself, it gives me 25? The answer is no. Negative 5 also multiplies by itself to give you positive 25. So the square root of 25 is actually positive 5 and negative 5, so we denote it by this plus or minus symbol. So when I'm writing my solution, this is how I say it. I say x is plus or minus 5. So there's actually two solutions here. So when we're taking the square root of something, we need to account for the positive value and the negative value. So keep that in mind when we're solving these quadratic equations right here. So letter A wants me to solve it. X squared plus 4 equals 0. I'm trying to get x by itself, so I need to subtract 4 from both sides first. That gives me x squared equals negative 4. Now I can take the square root of both sides. I get x equals, don't forget that plus or minus sign. Remember, this is the square root of negative 1 times 4. Square root of 4 is 2. Square root of negative 1 is I. Taking the square root of everything under the radical, so the radical has disappeared. So my answer to this quadratic equation is plus or minus 2i. So x equals 2i. X also equals negative 2i. Letter B. Solving for x once again. Trying to get x by itself. Add 11 to both sides. 2x squared equals negative 47 plus 11 gives me negative 36. Dividing both sides by 2, I get x squared equals negative 18. Once again, take the square root of both sides. So x equals plus or minus. Now I'm simplifying the square root of 18. I know I've got my negative 1. And now I want the biggest perfect square that goes into 18. That is 9 times 2. So taking the square root of 9, I get 3. Square root of negative 1, I get I. I cannot take the square root of 2, so it must stay under the radical. So my answer to this quadratic equation is positive 3i square root of 2 and negative 3i square root of 2. So I hope that makes sense that I need to account for my positive value and my negative value. Last thing, example 7, finding zeros of a quadratic function. Says find the zeros of f of x equals f of x, or 4x squared plus 20. When it wants me to find the zeros of a function, it wants me to set my function equal to 0 and solve for x. I'm finding out which values of x give me 0 for my function. So I set my function equal to 0, solve for x. So I'm subtracting 20 from both sides. 4x squared equals negative 20. Divide both sides by 4. X squared equals negative 5. Now I can take the square root of both sides. X equals, don't forget your plus or minus. There's no perfect square that goes into 5, so I cannot break that down into anything. But I can take the square root of that negative or negative 1 to get I, and then the 5 must stay under the radical. So the zeros for this function are x equals I square root of 5 and x equals negative I square root of 5. That'd be my answer. Here's our assignment, pages 132 through 133, numbers 58 through 84 evens. Once again, if you have any questions, please let me know.